Okay, so maybe it's time to start. Are you ready, Nóra?
Yes.
Yeah, okay. So today's speaker is Nóra Szakács from the University of Manchester, UK, and she's going to talk about closure operators on group Cayley graphs and presentations of n-inverse monoids.
Okay, thank you very much, and thank you very much for the invitation. So I'm primarily a semigroup theorist, but this what I'm presenting has a little bit of universal algebra flavor, so I thought it would be appropriate for the seminar. Still, I will still need to talk about what inverse semigroups are and inverse. I will be restricting to inverse monoids actually, in fact, for most of the talk. So I assume lots of you have seen these definitions already, but I'm just going to run through them anyway. So sorry, this is already I just noticed a typo here. This should be a semigroup. So an inverse semigroup is a semigroup M, such that for all elements there is a unique inverse with these properties. And it's not obvious with this definition, but it's actually true that inverse semigroups form a variety with the operations of the multiplication and the inverse defined by these identities. So the first two identities just come from the properties of the inverse itself. And this third identity basically tells us that the idempotence of the inverse semigroup commute. That's another way of saying it. And this property is actually equivalent, this idempotent commuting property is equivalent to ensure the uniqueness of inverses, which is kind of the difference between requiring just these and having the first definition. So there's additional nice identities which I thought to point out. So for starters, the inverse operation is an involution, which you can, well, if you believe that these two definitions are equivalent, then this immediately follows from the fact that the A inverse is unique. And we also have that we can calculate a product of the inverse of products in the same way as we do for groups, which is quite nice. We can similarly define inverse monoids. I was actually going to define inverse monoids first because that's all I talk about in the talk, but I wanted only 3 identities and I didn't want the monoid identities in there, so I thought to shorten it, but then I had a typo. Anyway, so something that I will be using is, just as in the case of groups, every element of an X-generated inverse monoid, so an inverse monoid generated by a set X, can be represented by a term in, well, this is called a free monoid and with an involution, but really we only care about for what it is as a set, and as a set is just variables in X together with their formal inverses, and we form finite words, including the empty word from those, so just as with groups. And it's basically these additional nice identities which allow us to do that, so you can kind of replace the term algebra with its quotient. Okay, so we're in a variety, so because of that, there are free inverse monoids. And actually, free inverse monoids have a very nice model, and this is given by Munn, the model that I'm about to present. So there's lots of information here, so let's go step by step. So for starters, we have a fixed generating set X, and we also have here the free group on X. So this FGX denotes the free group on X. And then the elements of the free inverse monoid, according to the model given by Munn, are pairs where the first, well, I'll start with the second. The second component of the pair is just an element of the free group. And the first component is a finite subtree of the Cayley graph of the free group. So the Cayley graph of the free group on the generating set X is a tree. So a finite subtree is basically just any connected finite subgraph. And I'm also requiring, this should be a T, I'm also requiring that 1 and G, which are vertices in the Cayley graph of the free group, are vertices of my tree T. So basically, here's an example down here. So the blue, for instance, is a tree T, and the respective elements are, so this is my vertex 1, contains the vertex 1, and say this is my vertex G. So G would be here, basically the value of x1 times x2 in the free group.
x1 times x1.
Sorry, x1 times x1, thank you, in the free group. So that's x1 squared, but anyway, I'm writing it like that now. So that's the blue guy, and then I have the I have this green one, which is, again, it's just this tree, and then this is my vertex 1 again, so that's part of the tree, and then this is H, my designated second component. And then how does the product work? So basically the product is a semi-direct product style structure. So first of all, we have that the free group acts on its Cayley graph by left translations. And in particular, it acts on any subgraph of the Cayley graph by left translation. So this GU is basically U translated by G on the left. So if I do this to this particular example, then I have to make sure that what was 1 before now ends up in G. So I will have to move this here. And the product is what? So the product, the first component of the product, the tree, is the union of the two trees. So this cross that you see here. And the second component is G times H, but you can actually view this G times H as the image of H under the G action. So exactly where my second point ended up. This will be GH. So my new tree will be this cross with this designated vertex as my second component. So that is the free inverse monoid on X. Well, and how do we kind of understand what word it corresponds to? So if I have any term, so term is of the form, so remember, any element of the free inverse monoid, and in particular any X-generated inverse monoid, can be represented by an element of by an element of the free monoid with involution on X. So in particular, if I have say something like x1 inverse, x2 squared, x2 inverse, what I do is, starting from 1, I just traverse this word in the Cayley graph. I remember what subgraph I traversed. So I did x1 inverse, x2 squared. I should have pre-planned this. x2 squared, x2 inverse. I remember where I ended up. That's going to be my designated second degree, and whatever I traverse is going to be my tree. So this will be the element representing the value of this term in the free inverse monoid on X. And you can kind of think about if the multiplication works as you would expect. Because if I were to continue to traverse some elements from here, then basically that would exactly be the same as if I traversed those elements before and then translated it to that point afterwards. Okay, so I hope that's clear to everybody. It's kind of difficult to tell on Zoom. Right, so, oh, I didn't tell you, so the inverse, what is the inverse? Well, the inverse is what you would expect it to be in a semi-direct product type of thing. So the inverse of TG is just G inverse T, G inverse. And you can sort of imagine, so the inverse would be corresponding to the word that you would get if you were to basically write this word backwards and write the inverse of every edge instead of, so the inverse of this term will be x2 to the minus 2, x1 inverse by the identity that we had before. And that's exactly essentially taking this point, pretending that this point is the identity, that is what translating it by G inverse amounts to, and then reading the word backwards. So x2 inverse, x1 inverse. So that will be the inverse of it. Okay, and it's an inverse monoid with these operations, and it's the free inverse monoid generated by X. Right, okay. So if we look at this definition, I'm going to erase this now because it's a bit hard to see. Then basically what this structure uses is that we have a graph and we have a group acting freely on that graph. This is what we need to define this multiplication essentially. So in particular, we can replace the free group on X with any group generated by X and take the Cayley graph of that group with respect to the generating set and define the same type of multiplication. So here is what this construction does. This is called the Margulies-Meakin extension. It was defined by Stuart Margulies and John Meakin, I think about 30-ish years ago. And it's exactly what you would get. So what is this? Well, if we start with an arbitrary group, this is not going to be a free object in a variety, but it's going to have a universal property. So it's basically the initial object in the category of X-generated additional adjectives that I'm now skipping inverse monoids. So it does have a universal property. And so the next slide, I'm going to talk about what the additional adjectives are that go here. So, okay, so just to kind of think about what this could be. So there's a very obvious choice here. We choose a group G, that is what we start with a given generating set. So we choose a group and a generating set within that group. And yeah, so let's go with that. So there's definitely a group. So the way the group comes in is if we take an arbitrary inverse monoid, it always has what we call least group congruence. So basically, what prevents an inverse monoid from being a group is that X inverse is typically not 1. But if we make it 1, then it will be a group. So basically, if we quotient an inverse monoid by the congruence generated by pairs of this form, where X is an arbitrary element of the monoid, then the image will be a group, and this is actually the greatest group image of this inverse monoid. So every map onto a group has to factor through this one, essentially. Now, notice that the sigma class of 1, so sigma is the congruence, the least scope congruence, the sigma class of 1 contains all the idempotents of the monoid. Any idempotent is of this form, actually. This form. So it contains all the idempotents. But usually it contains more. An inverse monoid is called E-unitary if it doesn't contain anything but the idempotent. So when 1 sigma is exactly the set of idempotents of that. So for example, if we take the Margulies-Meakin expansion of a group G, so remember this had elements of the form delta G, where delta was an arbitrary finite connected subgraph of the Cayley graph of G, and G was an element of G. So this is a subgraph of, I'm going to call the Cayley graph of G gamma X with respect to this generating set X. So what is the greatest group image of this? Well, you can sort of convince yourself, well, first of all, this definitely maps onto, so MG definitely maps onto the group G by mapping a pair onto just a second component. And if you think about the kernel of this map, so everything that maps to 1 is just going to be everything of this form. So this is what's going to be the pre-image of 1 under this map. And this is actually, if you believe that this is the sigma map, the sigma class of 1 contains exactly elements of this form, where delta is a finite connected subgraph containing 1. Okay, and these are all idempotents. If you remember how we multiply 2 elements together, well, we translate the second graph by whatever is the second component of the first guy and take the union of the 2. So if we square an element of this form, it's just going to stay itself. So all of these are idempotent. So in this case, this also shows that this map actually has to be the sigma map because, well, it identifies nothing else to one but the generating pairs of the congruence, but it's actually also E-unitary because there's nothing else in the congruence in the congruence class of 1 but the idempotents. Okay, so we have a bunch of examples for E-unitary inverse monoids, and actually we can consider this category, which was again first defined by Margulies and Meakin, of all E-unitary inverse monoids, where the greatest group image is a prescribed group G, and we also fix a generating set for the group G, and we also assume that the inverse monoid itself is generated by the same set. So here's this definition. This is this category of all X-generated E-unitary inverse monoids with greatest group image G, and the morphisms are inverse semigroup morphisms fixing the generating set X. So we are assuming that the generating set is fixed. I'm not assuming, by the way, that the generating set is actually contained in G or in the monoid. I'm just assuming that there's a map from X to these algebraic structures, and the image of that map generates the algebraic structure. And then the Margulies-Meakin expansion of a group G is the initial object of this category. So it basically means that it maps onto it's mapped homomorphically onto any such unitary inverse monoid. By the way, I also want to point out that because I'm assuming that the morphisms fix the generating set X, it also means that there's at most one morphism between any pair of objects. And in fact, I'm only taking the objects up to isomorphism, so there's never two errors going in both directions. So it's basically just a bunch of objects, and some have a morphism between them in one direction and some don't. That's what the category looks like. Okay, is that clear so far to everybody? Okay, so yeah, feel free to stop me if not. I have absolutely no concept of like whether I'm going too slow or too fast because I'm not seeing anybody's reactions as I would in person. So let me know if there's anything that you want me to elaborate on. Okay, so so why are E-unitary inverse monoids important? Well, one of the reasons is that they have a beautiful description, a structure theorem, which is a classical theorem in inverse semigroup theory. It's called Macalister's P theorem. And I'm not stating it exactly, but this is the rough idea, is that every E-unitary inverse monoid can be built, and it's given how this is built, out of three things: a group G, which is actually the greatest group image of the inverse monoid, a semilattice Y, which is the semilattice of its idempotence. So remember I said the idempotence of an inverse monoid commute, which means they form a semilattice inside the inverse monoid. And the poset X containing this semilattice acted upon by G. Now, you'll notice that G and Y can be easily understood in terms of the monoid, but X is a bit mysterious. And there's been a lot of attempts to reprove this, well, successful attempts to reprove this theorem, motivated by giving X a meaning, basically. And one of these was done by Ben Steinberg, who basically gave a proof of Macalister's theorem where X is a certain set of connected subgraphs of the Cayley graph of G, and Y is the semilattice of those graphs in X which contain 1. And the semilattice operation is it's not the join actually. It's something in general it's something a bit potentially bigger than the join. So it's not that clear in terms of the connected subgraphs. It is kind of clear if you read Ben's paper, but it's not as clear that I can actually say it now what that is. But this is the basic idea, is that both Y and X are realized by certain sets of connected subgraphs. So for example, for the Margulies-Meakin expansion MG, well, the group G is just this G, the greatest group image. In this case, Y will actually be just, so I'll tell you what X is. So X will be all finite connected subgraphs. So here this certain corresponds exactly to finite. In general, you're not restricted to finiteness. and y is exactly those graphs in X which contain 1. Containing the vertex 1. So 1 is a vertex of the Cayley graph. That's what I mean. So that is one way to mechanistically represent MG. And so basically this is so the idea of Steinberg, I'm sort of looking through the audience really quickly to see, well, there's some people that this will say something to. So basically the certain set of connected subgraphs are exactly the embedded copies of the Schützenberger graphs of the inverse semigroup, if that means something to you. I'm not going to explain what that is, but basically these Schützenberger graphs have a lot to do with solving word problems in inverse semigroup presentations. Maybe that's worth saying. Okay, so basically the first thing that I'll do is we will rephrase this approach of Ben in terms of closure operators on subgraphs of the Cayley graph of G. So basically a certain set of connected subgraph will actually be a set of closed subgraphs with respect to some closure operator. And it will turn out that actually all closure operators with certain properties will arise this way. So this will be the next bit. So to fix some notation, G from now on will always be an X-generated group. Gamma X will always be its Cayley graph with respect to the generating set X. C sub X will be the set of connected subgraphs of gamma X, not necessarily finite, the set of all connected subgraphs of gamma X. By the way, a Cayley graph, of course, so a Cayley graph will have an edge X between 2 points, then it will have an edge X inverse coming backwards. I'm only considering subgraphs which actually contain both pairs, so like symmetric in this sense. And of course, I'm only drawing the positive edge as is usual. And then this operator C, this will be just a closure operator on the poset of the set of connected subgraphs ordered by inclusion. So I'm going to denote the closure of a graph like this. And I'm going to say that a closure operator is G invariant if this, so just a reminder, the set of a closure operator is uniquely determined by its set of closed subgraphs, by a set of closed sets in general, which are these closed subgraphs in this case. So I can define what it means for a closure operator to be G invariant in terms of its closed graphs, and it's exactly if its set of closed graphs is invariant under the left action of G. And in particular, what this ensures, if I want to understand the closure of, it's not what I wanted to write, the closure of G delta, then that is the same as G of the closure of delta. So this is where I'm using this property, and the closure operator, this is a well-known thing. Some people call it finite tree, some people call it algebraic. I don't know which is more common. So closure operator is, I'm going to use finite tree if it's determined by its finite sets. But basically, this is the formal condition. It's the union of the closures of all those of all those finite sets which are contained in delta. So typical like finite tree closure operators, which is where algebraic comes from, is taking the generated substructure in some algebra. And as usual, again, I'm going to call an element of the poset compact if it is a closure of a finite element. So it's so a subgraph is compact if it is a closure of a finite subgraph. So in particular, compact graphs are closed themselves. Okay. And so with that notation, we're going to take a G invariant finite tree closure operator on this poset of connected subgraphs of the Cayley graph of G. And then associated to that, we have an inverse monoid, which I'm, sorry, I forgot to say, but this closure operator should be C. And so the inverse monoid, I was going to say it's MC, actually, I think. MC is defined the following way. So it's very similar to the Margulies-Meekin expansion. It's actually, the Margulies-Meekin expansion will be a special case of this. So the elements are pairs. The second component comes from the group G, and the first component is a compact subgraph of gamma X with 1 and G contained so these are again vertices contained in delta. So it's a closed graph, but it's also compact. It's a closure of a finite thing. And then the product is given like this. So instead of just doing what we did before and here in the first component, just taking the union of delta and g psi, we take the closure of that because it has to be closed. And then the inverse is actually just what we had before. Remember our closure operator is g invariant, so this will be a closed subgraph whenever delta was. And you can check that this is an inverse monoid with these properties, and furthermore, it is a unit, and the E interness is proved the exact same way as I explained in the Margulies-Meakin expansion. It's also X-generated, and the fact that it's X-generated is ensured by definitoriness of a closure operator. So if I have an element delta G, so delta is the subgraph of the Cayley graph of my group. Here is 1, here is G, and it is the closure of some finite subgraph. And I can assume without loss of generality that my finite subgraph also contains 1 and G. And then I just take any path traversing this finite subgraph. I read the labels of that path, and that word in X and X inverse will represent this element. So it is X generated as well. Right, and so this is what I said. So it's also E unitary X generated. And is there anything else that I wanted to say here? I think not. Okay, so given a closure operator, then we it actually gives rise to an inverse monoid. There's also a way to go back, but before I say that, I'm just gonna actually define another category. So just to remind you, I had a category of X-generated E unitary inverse monoids with greatest group homomorphic image G. And now I'm going to consider the category of all closure operators of the properties that we had. So I have an X-generated group G, and I consider this category CGX, where the objects are the definitory G invariant closure operators on this poset of connected subgraph of the Cayley graph. And the morphisms is, again, between each pair of objects, I'm going to have at most one morphism, and there's going to be a morphism from the closure operator C1 to the closure operator C2 if every closed subgraph in C2 is also closed in C1. So basically, an equivalent way to say this is that delta C1 should be contained in delta C2 for any delta. This is equivalent to that. Okay, and so one of the theorems, one of the main theorems of the talk is that this category is equivalent to the category of X-generated unitary inverse monoids. And so the functor going from here to here, so closure operators to inverse monoids is exactly, so if we have a C, then we are associating the monoid MC to it. And to go from here to here, the inverse of the functor. So this is kind of, it uses Ben's idea, and Ben's idea about Schützenberger graphs actually uses Stevens' procedure. Now I'm not going to explain in detail either of those things, but just to give the main idea. So if I have such a monoid, so if I have any monoid contained in the object set of this category, then I'm going to associate to it a closure operator CM. Is defined by, and I'm going to define by its set of closed subgraphs that uniquely defines it. So it's set of closed subgraphs. So I'm going to say that delta is closed if, so delta is so here's my group Cayley graph, and here's my subgraph delta. And if I take any vertex in delta, so for all U and V delta, and for all words W1, W2 in X and X inverse, such that W1 and W2 have the same value in M, I want the following property. If I can read from this vertex U, I can read W1, then I also want to be able to read W2. And notice that actually, if W1 and W2 have equal values in M, the group that I'm drawing this in is the greatest group image of M. So in particular, it is a homomorphic image of M. So in particular, this also forces W1 to have the same G value as W2. So not only do I have that W2 has to label a path from U as well, it will actually end up being parallel to W1. So this is what it means for delta to be closed. This is the closure operator we get from delta. And where Stevens' procedure comes in, really, I remember I mentioned that this has to do with solving work problems in inverse semigroups. That sort of comes in by saying that if I have an inverse monoid given by a presentation, then it doesn't matter if I'm requiring this property or if I'm only requiring this property for pairs W1, W2, which come from the presence, which are relations in the presentation. And so then you can kind of use this to, well, to approach the work problem by basically iteratively constructing these closed subgraphs using pairs of relators in the presentation by basically taking some subgraph which is not closed and then approximating its closure by adding new and new paths so that this is satisfied. That's the main idea. Okay, so any questions? Okay. If not, then I will move on to the bit of the talk that I actually mentioned in the abstract, which is about F-inverse monoids. So I should say the bit about linear inverse monoids, this actually came about by a conversation that I was having with Mark Cambitis, who were actually thinking about when subgraphs of the Cayley graphs arise as Schützenberger graph of some E-unitary inverse monoid, and that turns out to be settled. So this never ended up kind of making the project that we were working on, but then it turned out to kind of strongly correspond or relate to this other thing that I will talk about, which is related to F-inverse monoids. So what are F-inverse monoids? So this is something I didn't say yet, but inverse monoids are naturally equipped with a partial order. There's many ways to define it. This is one definition. Don't think about it too much. The important thing is that there is a partial order. Another way I think maybe the most natural way to think about the partial order, which you don't need to know anything besides what I already said, is you have the semilattice of idempotence sitting inside the inverse monoids. And of course, since that semilattice generates partial order, you can, so basically this partial order on the inverse monoids is an extension of the partial order which on the semilattice, which the semilattice structure defines, in a way that it's compatible with multiplication. So this is actually one way to obtain this definition. Now, an F-inverse monoid is an inverse monoid which has a greatest element in every sigma class. So remember, sigma is the greatest, is the least group congruence. So every sigma class has to have a greatest element, and then the inverse monoid is F-inverse. So for example, the free inverse monoid on X. So remember, this consisted of pairs TG, where T was a tree, and 1G were vertices of the tree in the Cayley graph. I didn't write it down. A finite tree, nonetheless, and 1G were vertices of the tree. So in this case, the sigma relation, remember the sigma map for Margulies-Meekin expansions is just mapping onto the second component. So the sigma class of TG is well, TG is in sigma relation with UH if and only if they share the same second component. Now, the natural partial order here is actually having the same second component and being comparable in the first component. But actually the order goes the opposite way. The reason for this reverse of the order is, if you remember, the way we multiply in this free inverse monoid is we take the union of graphs. So multiplication corresponds to the union, whereas normally in semilattices you would think of this as a meet operation. So this is why there's this reverse. So in this case, if we take an arbitrary tree, so something like this, and say this is 1 and this is G, so this is TG, then the greatest element in the sigma class of this graph is going to be, well, first of all, it's going to have to be sigma related. So it's going to be a tree, which again contains G, and of course it contains 1. And furthermore, it should be a tree which is contained in my tree T, and is also minimal in the sense that any other tree which contains both 1 and G will have to contain my tree. That's what it means to be maximal in the partial order. It's minimal and as with respect to containment. So this will just be basically, well, I just take the geodesic from 1 to G, so the reduced form of the representative of G in the free group, and that will be the maximal element in the sigma class. And I'm able to do this because my graph is a tree. If I take the Margulies-Meakin expansion of a group which is not free on a given generating set, it will never be F inverse, because I will never be able to take a unique smallest subgraph containing two vertices. Okay. So F inverse monoids are generally not closed under morphic images because, well, the free inverse monoid is F inverse and most inverse monoids aren't. But if we add an additional operation, which, so this operation M, which is a one variable operation, and to every element, it assigns the greatest element in its sigma class, then they form a variety with respect to these operations. And this was, I think, first observed by Michael Kenyon, and then formally, I think it was first proved in the paper that I'm going to cite later by Karl Einder, Anya Gurdjevtseva, and Maria Sendre, but they can correct me if I have that chronology wrong. But anyway, so these are the defining identities. This looks like it's not an identity, but it is an identity. If you remember, the definition actually only used equality there, an operation. So you can rewrite this as an equality as well. Additional nice identities, which I wanted to say. So if I have something of this form, so A, maximal element of the sigma class is B times C, and the maximal element of that, we don't have to have the M there. It's quite clear to see because these two guys are sigma related, because sigma is a congruence and M respects sigma. So this is true. And I also have that the maximal element of the sigma class of an inverse is the inverse of the maximal element of the original guy. So these two nice identities allow us to represent every element of an X-generated F inverse monoid by a term of this form. So basically I have a bunch of words coming from my free monoid with involution, and in particular these words can be empty, and then I can put an M on any word, but I don't need to have nested M's because of this first identity, and I can put the M outside. I don't need to have like an M and then an inverse on top of that because of the second identity. So every element can be represented in this form. Okay, so, and this is the paper that I just mentioned. So Karl Anya and Maria gave this following description of the X-generated free F inverse monoid. So remember I said that the free inverse monoid on X was F inverse, but it's not the free F inverse monoid, because in particular, I'll just write it here. So in the free inverse monoid on X, I have that if X is one of the generators, then XM is actually just X. So that will be just a single edge in the Cayley graph, the maximal element to corresponding to that sigma class as itself. Now, this is not a relation that, or this is not something that would hold in the free F inverse monoid. So that is something more general, and in particular, the free F inverse monoid generated by X will not be X generated as a free inverse monoid. So if you look at the definition, it's actually a bit hard to spot where it differs at first sight, where it differs from the definition of Mon trees. But this is the bit here. So everything is essentially the same, except we're dropping the condition about connectedness. And that allows us to define the maximum element of the sigma class of a tree. Well, this is no longer a tree. This is a union of different trees, different finite trees. In the Cayley graph is just going to be the two vertices, 1 and G, and nothing else. And so how the multiplication works in a similar way, but how is this X generated? Well, if I have a term of this form, so U1, V1M, U2, V2M, and so on, then basically this will correspond to this a pair where I start from 1, I traverse U1, as I did before, and then instead of traversing V1, I basically make a jump of length V1. So instead of traversing it, I just jump to where I would go if I had traversed it. So this will point to basically the free group value of these words. And then I continue this. So now I again traverse something, and then I jump. So this will, of course, not give a connected subgraph in general. And again, I keep track of where I landed in the very end, and that will be my G. So in particular, this is just represented. I take any representative of G in the free group. So if this is represented by some word W, then this will be just M, W, M. And I forgot what I was going to say, but yeah, so this, I remember. So these things are called journeys in this paper that I mentioned. So this is the journey spent by this term. Okay, so similarly as before, we don't need the free group to be free here. We can take any group generated by X. There is a natural analog of the Margulies-Meakin expansion, which they prove a natural analog of the universal property of. So it's basically going to be the initial object in the, sorry, this is supposed to be category, it's not a variety. Category of X-generated F inverse monoids with greatest group image G. Okay, and then a lot of things that we've done before, actually everything that we've done before, we'll just go through. There is a bit more work to do because there's no Stevens procedure yet for F inverse monoids, but basically what we do will yield that there is a Stevens procedure. So this Schützenberger graph thing that I mentioned but didn't go into details about will also follow from the fact that everything grows true. So we do exactly the same thing as before, except we are now considering the set of subgraphs of the Cayley graph rather than the set of connected subgraphs. So again, we drop connectedness and we take we look at closure operators in just a set of subgraphs. And then again, we can define, given a G invariant finite free closure operator on subgraphs, no longer connected, we can define an X-generated F inverse monoid in the exact same way as before. So these three are things that we had basically just copied over exactly from the unitary case. And now we also have an operation corresponding to a maximum element in the sigma class, which is going to be just the closure of the of the subgraph on two vertices, 1 and G. And this is, again, well, it's an inverse monoid. The proof is very similar. It's actually F inverse. That's also clear. The way it's X generated, again, is quite similar to what we had before. Again, delta is a compact subgraph. So it's the closure of a finite subgraph. Now that finite subgraph might not be connected, but I can still traverse this subgraph using journeys. So basically I traverse whatever's here and then I jump, and then I traverse whatever's here and then I jump. and I make sure to end in the right spot. So it's still X-generated in this variety. Okay, so the theorem that I'm going to state is going to be very similar to what we had before, that the category of X-generated F inverse monoids with a given greatest group image is equivalent to the category of closure operators on this poset. But now I'm actually going to spend a slide on giving the inverse functor. So that the previous was how we define an F inverse monoid coming from a closure operator. And then this one is, if we have an F inverse, like this is meant to be monoid. So an F inverse monoid M with M over sigma equal to G, then we can associate a finite tree G invariant closure operator on the subgraphs of the Cayley graph gamma X of G. And again, we can define the closure operator by defining its closed subgraphs. And it's the same as we had before. So now I have two terms, W1, W2, which are terms. So they have these potential M's in them, but I can still talk about the journey that they label. So if I have any two terms, W1 and W2, representing the same element in M, and I have a G, and then delta is closed if G contains the journey labeled by W1, if and only if it contains the journey labeled by W2. And again, this condition implies that W1 and W2 have the same value in the root. So those two journeys do, if those two terms are equal, they do exist in the Cayley graph and they do map into the same point. And then this is true for inverse monoids as well. What allows us to talk about presentations and word problems is the fact that if M is given by a presentation in the variety of F inverse monoids, then in this description, or I think I mentioned this, but I didn't write it down, for inverse monoids, it actually suffices to consider W1 and W2 to be pairs of relators in the presentation. So not two arbitrary terms that represent the same element, but just two terms which appear in my presentation as a relation. Okay, so what else do I have here? This is the theorem that I already stated. These two categories, so the category of X-generated F inverse monoids with the greatest group image and the category of closure operators are equivalent. And so in particular, if I have two terms, W1 and W2, or maybe I just have I just have a single term, W, and I have M, an X-generated F inverse monoid. Then if I first associate to W, basically what do I want to say? Yes, so basically I first go from here to here. Now the way I go from here to the category of F inverse monoids to the category of closure operators is basically I take the journey spanned by W, so it's the subgraph labeled by the journey starting at 1 in the Cayley graph, and I take the closure of that. This will be an element of sub gamma X, and it will actually also be a compact subgraph there. And then I can consider the pair WC and then the G value of W. And this will be the corresponding element so this will be the corresponding, so I have a corresponding closure operator to M. I consider the closure of W with respect to the closure operator, and this will be the element corresponding to W once I go forward and back with this functor. So basically that means, this is a long-winded way of saying that it's W1 and W2 have the same M value if and only if they span the closure, they span journeys which have the same closure and they're G equivalent. So if these two pairs are equal. And so in particular, if M is given by a presentation, then I can understand this closure operator just in terms of the relators because of the previous proposition. So given W, I can approximate, and if I'm lucky, I can maybe on the nose describe what the closure of W is. And then I can understand when two elements labeled, when two terms define equivalent and equivalent elements by basically just comparing the closures of these two terms in the group Cayley graph. So, so this, if you know Stevens' algorithm and Schützenberger graphs, this will be very familiar. Well, basically, in this slide, I just basically explain everything again that I said before. So if I have an inverse monoid presentation, and G is its greatest group image, then I define the F-Schützenberger graph of a term W to be the smallest subgraph of the Cayley graph of the group with respect to the generating set X, which is closed in the closure operator corresponding to M. And again, that closure operator is something that I can understand in terms of the relations alone, and contains the journey labeled by W starting at 1. So that is basically, this is what I defined previously to be the closure of this journey labeled by W. And then there's a theorem. So basically, the second part of the theorem is exactly what I said before. And the first part of the theorem, this is analogous to the theorem about Schützenberger graphs for inverse monoids. Again, if you don't know what that means, don't worry about it. You can just take the theorem as is. It again follows from understanding the partial order on these inverse semigroups, which comes from closure operators. So given two terms, W and W2, we have that W1 is greater than W2 and M if they have equal G values, and the F-Schützenberger graph of W1 is contained in the F-Schützenberger graph of W2. Again, this is meant to be W2. And so in particular, they're equal if and only if both contain this fold. And so this is one way to try and approach the word problem. You start approximating both F-Schützenberger graphs by adjoining these journeys as you need to. And then once you can read both journeys in both approximations, you know that they're equal. Okay, so I think this is all I have time for. I had an example here, but I'm going to skip that. Well, I'm not going to explain the example, but I'll leave it up for you to read. And I think I'll stop there. And thank you very much.
Thank you very much.